If you walk into a large retailer today or browse the web looking for a Wi-Fi access point, you're met with a large variety of choices. 802.11n, MIMO, 802.11ac, peak speeds of 600 megabits per second, oftentimes hard to digest. Let's look at what these different letters mean and how things evolved in the Wi-Fi space. Wi-Fi was originally standardized back in 1997. It can actually trace its origin back to a 1985 ruling that released something called the ISM band, or 2.4 gigahertz and 5 gigahertz spectrum, for unlicensed use. The original Wi-Fi spec, also known as legacy Wi-Fi, ran at a whopping 1 or 2 megabits per second. It was largely viewed as a cute but uninteresting access mechanism for the network. One could simply plug in a wire to an Ethernet network at speeds of 10 or 100 megabits for a relatively good performance, or embrace this lossy, oddly performing 802.11 standard. The 802.11n standard governs both the physical layer, how we encode or send bits, as well as what's called the MAC, or the Media Access Control Layer, how we react or sense to collisions, as we saw earlier. The term Wi-Fi actually did not come about until 1999 by a group called the Wi-Fi Alliance, which was a trade group set up to promote 802.11. Wi-Fi drew its roots, of course, from operating in unlicensed bands. In its infancy, this meant operating in the 2.4 gigahertz and 5 gigahertz ISM bands. The bands were split up into channels, and the 2.4 gigahertz band being divided up into channels 1 to 11 for the US, or maybe a few more external to the US. And the much higher channel numbers, 36 and higher, applied to the 5 gigahertz band, although not always ordered the same. While there was considerably more spectrum in the 5 gigahertz band, accessing said band was a lot more difficult due to challenges due to radio construction and the wireless environment. Notably, while the 2.4 gigahertz band has 11 potential channels, only 3 of those channels are non-overlapping, or what we would call orthogonal to one another. Nearby channels in the 2.4 gigahertz space, such as channel 1 and channel 2, are not wholly separated, and hence partially interfering with one another, making scaling in the 2.4 gigahertz band difficult, as we really only have 3 independent channels. However, back in 1997, when 802.11 had achieved standardized status, scaling was much less important than beginning to achieve critical mass. Extensions to the core 802.11 spec were immediately planned, and 1999 saw the introduction of 802.11b, which some of you may still be using. This operated in the 2.4 gigahertz band and had dramatically faster speeds, going up to 11 megabits per second. You might ask, though, what happened to the 802.11a, which is a great question. The answer is that 802.11a actually also came out in 1999. 802.11a operated up in the 5 gigahertz band, and it brought considerably higher speeds with 54 megabits per second and utilized the technology called OFDM. This actually got you halfway up to what the wired networking speeds could offer. Unfortunately, as they found out, 5 gigahertz tends to be much more difficult to operate in part because the electronics tended to be more expensive at the time, and also many environmental issues tended to impact my performance at 5 gigs. In short, what happened is frequencies at 5 gigahertz tended to be attenuated much more, going through concrete or steel walls, or even going through high efficiency windows. While 802.11a faltered at the onset, 802.11g brought concepts from 802.11a back down into the more palatable 2.4 gigahertz band. The end result was that we got the same 54 megabits per second speed, but without all the headaches that the higher frequencies imposed. 802.11g actually did not become standardized until 2003, although that didn't stop people from offering devices much earlier than that. Intermediate 802.11 standards actually have occurred in between then, refining management and other properties which you don't actually go out and buy, but impact all of your Wi-Fi adapters. That trend radically accelerated with the development of 802.11n, the successor that did not officially become approved until 2009. Now, at the time, demand was so great for faster wireless that we'd already seen with 802.11g that frequently shelves were dominated by gear that purported to offer 802.11 draft end support. 802.11n is interesting in that it operates in both the 2.4 and 5 gigahertz bands. And when we operate exclusively in 5 gigahertz, we can support peak speeds of up to 270 megabits per second or 540 megabits per second. Not bad. Now for the 540, we actually need to add in a new technology, something called MIMO, or multiple in, multiple out, where we can both send and receive at the same time. 802.11n actually gets those speeds by cheating a bit. It gets that by bonding different channels together. So to get those faster speeds, instead of using a standard 20 megahertz channel, it actually ends up using 40 megahertz of channels. Most recently, 802.11ac devices have begun to emerge. 802.11ac offers the potential for up to 1.3 gigabits per second, even far outpacing 802.11n when accounting for all of its various MIMO potential. 802.11ac continues the same trends of 802.11n by allowing for more channels to be bonded together to achieve its faster data rates. Finally, in closing, range on 802.11 tends to be fairly good. We talked earlier how it's roughly medium range. That means that we can offer connectivity up to a couple hundred feet away. And in fact, 802.11n, when we operate in the 2.4 gigahertz band, can give me even 200 feet in terms of connectivity.